Okay, so there is four kinds of nuclear radiation that we need to know about in order to kind of explain a lot of the things we're going to be looking at over the course of this unit. The very first type is called alpha radiation, or alpha particles. And what an alpha particle really is two protons and two neutrons stuck together. It's really, that means it's a helium-4 nucleus. So the symbol that we write for that is it got a mass number of 4, and there's two protons in there, and that means that it's helium. Another way of writing it is to say that it's 4 and 2, and since to remind us that it's actually called an alpha particle in this case, is we use the Greek letter alpha, which is kind of like a little curlicue, like a little fish almost. Okay. And if you think about on the NZ plot, we have got neutrons along the up and down axis and protons along the left and right axis. If we start off in this square right here and we give off an alpha particle, that means we are losing two neutrons. So we're going to go down 1, 2 squares on the NZ plot, and we're also losing two protons. So we're going to go left 1 and finish up 2 squares to the left. So it's down 2 and left 2. On the NZ plot, an isotope that gives off the alpha particle goes down 2 squares and to the left 2 squares. The next kind of radiation we should know about is what's called beta radiation, or beta particles. And what a beta particle really is an electron. Now, if you want to know how it is that an electron can come flying out of the nucleus where there aren't any electrons, you'll have to talk to me after class or something and I'll explain it to you. But for now, we'll say for now that it's got no mass and -1 is its charge, and so a beta particle is really an electron, so sometimes we'll use just an E. In other cases, we'll use the Greek letter beta to indicate that it is in fact a beta particle, and that's like a B with a little tail on it. You can use either, it doesn't make any difference to me. And on the NZ plot, if you start off in this square right here and you give off a beta particle, what happens is you go down 1 square and then to the right 1 square. You lose a neutron and gain a proton, which means you go down 1 and left 1. The third kind of particle that we should talk about is what's called a positron, which is something you probably have never heard of before. A positron is really a positive electron, which really doesn't make sense. So it's got no mass, a +1 charge, and we symbolize it by using a beta sign with a little plus as like an exponent there. That means that is a positron. And a positron on the NZ plot, if an isotope is located in this square and gives off a positron, that means that it is going to move up 1 square and to the left 1 square. It's, in a sense, it's gaining a neutron by moving up 1 square, gaining a neutron, and losing a proton. It goes left 1 square. The last kind of radiation we should talk about, and this is less important, you don't need to know as much about this, but we should at least hear of it once, is gamma radiation. Gamma radiation has got no mass and no charge, and that means we don't usually write it into nuclear reactions because it doesn't change anything. And the symbol for gamma is like this long, skinny, fish-looking thing. It's upside down, though. Gamma radiation is radiation that accompanies the emission of one of these other particles. So if an atom gives off an alpha or a beta or a positron, it will usually also give off some gamma as well. And you can think of it, I like to think about gamma radiation as the nucleus kind of settling back together again after it kicks out a different part. So if it shoots out an alpha particle, there's kind of a chunk of the nucleus missing, and then as it settles back together into a nice compact nucleus after losing that part, it gives off gamma radiation. So now that we know about these different types of radiation, we can look at the NZ plot in sort of a whole new way. For example, that isotope of tin that we were asked to plot on our assignment after the lab where we colored this thing in, we had 50 protons and 80 neutrons. I think that was right about here on the chart. That isotope just simply has too many neutrons, or you can think of it as having too few protons. It wants to move down and to the right. And so we can say now, as you understand these different types of radiation, that all of the isotopes, any of these stable isotopes that fall up into this region where they're kind of above and to the left of the band of stability, are going to give off beta radiation. Because beta radiation has the effect of, each time you give off a beta particle, it takes you down 1 square and to the right 1 square. Those elements, those isotopes that fall into this region have got to lose neutrons and gain protons, so beta radiation is the perfect way to go. They'll give off beta radiation moving down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, over and over again until they come into the band of stability and change into one of those isotopes that is stable. Similarly, the isotope we were asked to plot where we were at 60 and 60, this is an atom or an isotope of neodymium on that lab. It's down here in this area below the band of stability, in the lower right-hand portion of this chart. Those have got too many protons, they're too far to the right, or too few neutrons, depending on how you want to look at it, and they want to move up into the left, and so they give off positron decay. These guys shoot out positron particles because each positron they give takes them up one, and when they shoot it out, it takes them to the left one. They gain a neutron and lose a proton. So this isotope of neodymium here would probably be the type of isotope that gives off positron radiation, moving up and left with each particle it gives off. And the really big ones, the whoppers, this francium-216 that we were asked to plot way up there, the atoms that are just simply too large to be stable give off alpha radiation, because alpha radiation contains 2 protons and 2 neutrons. So each time that this isotope gives off an alpha particle, it loses 2 neutrons and 2 protons, takes it down 2 and left 2. So after one alpha emission, it would be there. It's still not stable, so it'll do it again, give off another alpha particle. It ends up here, still not stable, and it'll continue to do that until it is small enough where it can form a stable isotope. So now that we know about the particles, we can look at the NZ plot and make a prediction about what types of radiation, which types of particles each of these unstable isotopes will give off in an effort to become stable. So now let's look at how we can write reactions to depict these different decays that can go on. So something that you got to know before we start doing anything is that chemical reactions are written with an arrow in the middle, and that separates what's there before from what is there after. So we have kind of a story written out. This stuff changes into this stuff. And so let's start off with just an example here. If I have an isotope, a nucleus of actinium-227, actinium has got is element number 89. Okay, actinium-227 is one of those elements that is going to do beta radiation, and so beta radiation, a beta particle is going to come out of this thing. So we say that, okay, we start off with actinium-227, and then afterwards there's going to be a beta particle. And what else? If you're asked to figure out what else, that's kind of what we're trying to work out here. If we're going to fill in the blank, what's the other thing that's going to be left over? When this actinium-227 shoots out this beta particle, what's left? Now the rule is that whatever is there before has got to still be there afterwards. We can't lose any parts. And so if there is a total mass of 227 before, and the total mass afterwards has got to be 227. And since 0 of it is in the beta particle, then that means it's all 227 have got to be in whatever the other part is going to be here. And then also our charge has to be conserved. We have 89 positives here, and the beta particle is -1. That means that whatever this other particle is, it has to have plus 90, so that 90 plus -1 balances out the 89 that are on the other side. And the 90th element is thorium. So actinium-227 undergoes beta decay, and it's going to change into thorium-227. Now, a couple of terms that we can introduce here about these reactions. Well, these are nuclear decay reactions. When we have a decay, we call the thing that is decaying the parent. So the parent decays into some particle. In this case, it's a beta particle. And then this other isotope that's left over when we're all done is called the daughter. Now, I'm not exactly sure why it's called the daughter and not the son or the nephew or anything like that, but it just is. It's called the daughter. So we have a parent isotope of actinium-227 decaying via beta radiation into thorium-227. Let's do a different one with a different type of radiation. Radium-222. Okay, radium is element number 88. And its symbol is Ra. Radium-222 is a really, really big isotope, and those tend to give off alpha particles. And alpha particles, as you just found out, are when we have got 2 protons and 2 neutrons stuck together. Now, if the radium-222 gives off an alpha particle, the other thing that's got to be left over has to have a mass of 218, because 218 plus 4 equals 222. The mass on the left side of the arrow has to be the same as the total mass on the right side of the arrow. And the same thing goes with the charge. This must have an atomic number of 86, so that 86 plus 2 gives us the 88. Element number 86 is radon. And that's the end. So we could write this reaction and say that radium-222, that's this stuff right here, gives off an alpha particle. And when it gives off an alpha particle, what's left over then is radon-218. So we've done a beta particle and we've done an alpha particle. Let's do one where we give off a positron. Sodium-22 is one of the isotopes that gives off positrons. So if sodium-22 comes along and decays by giving off a positron, and this is the symbol again for positron, what will be the daughter isotope that's left over? The daughter would have to have a mass of 22, because 22 plus 0 equals 22. And the positive 1 on the bottom by this positron means that the charge on the daughter has to be 10, because 10 plus 1 equals 11 from the other side. Element number 10 is neon, so sodium-22 decays by a positron radiation into neon-22. All right? Now there's one last way that these can be presented to you, and it can be, can you find the other particle? So if we did an example where, say, we started off with thorium-234. Thorium is element number 90. And I said thorium-234 has decayed and it's changed into protactinium-234. Protactinium-234 looks like that. What's the particle? What kind of radiation did it give off in order to do that? Well, the mass didn't change. That means the particle has got to be massless. And the charge went from 90 to 91, which means that in order to conserve that charge, in order to have the same charge on both sides of the arrows, the charge must be -1 for our particle. So the particle that has got a mass of 0 and a charge of -1 is a beta particle. So that's just another twist that we can do, where we give you the parent and the daughter and we ask you to find out what type of radiation, what kinds of particles did that.